our next speaker, Anton Antonov. So Anton is an applied mathematician, PhD with 30 years of experience. And in the last 10 years, Anton focused on developing machine learning algorithms and workflows for different industries. So music, movies, recruiting, and healthcare. So with that, I'll turn it over to you, Anton. I can see your screen. I can't hear you yet, though. Or you might be muted.
Yeah,
there we go.
I was muted. All right, so I'm going to give a very quick overview of the presentation. What is the big secret or the little secret about it? So in the next 3 minutes. So first of all, you'll see a bunch of screens, but the main presentation is here. This is the main presentation. This is the mind map for the presentation. The main materials are here. And then I might go to some of the other desktops in order to show what is going on. All right, so what I'm going to be showing is how we generate images for a certain machine learning type of algorithm or workflow. This is latent semantic analysis. And these images happen to be mandalas. And then we generate them within Python. And after we generate them within Python, we make the corresponding objects. We propagate them through the different environments. Mathematica, they're already in Python. And then we do some latent semantic analysis objects related to this. Then we extract the topics. Or this is what this dimension reduction is. Then we do some basis interpretation, and then we show that we can actually approximate, with this basis we have derived, we can actually approximate some image we haven't seen before. Okay, so how this looks in R, right? So you can see this is where, hopefully you can see it. So yep, this is where, okay, great, thank you. So this is the HTML version of the R notebook, right? So here I'm starting the Pandas session. I make my mandala collection in Pandas. Then I getting these mandalas in Pandas. I do some image manipulation, and then I start my latent semantic analysis objects wherever they are. And then we apply 2 different dimension reduction algorithms: singular value decomposition, non-negative matrix factorization. So after that, I want to interpret the obtained basis. You can see this is an average mandala, and these are corrections on the average mandala. This is this is the singular value decomposition. With the non-negative matrix factorization, we get a different type of basis, which is actually more thematic. So this is the deconstruction. The title of the talk being random mandalas deconstruction. This is how we deconstruct them into these 2 different ways. And next, we create a new mandala inside Python. We propagate it to R and do the corresponding manipulations we did for the training images. And then we try to approximate it. Oh, this looks worse here. Okay, so I try to approximate it with the singular value decomposition, and this is the result. This should, this is the Python notebook, but I know, yeah, okay, so this was the original image. This is the approximated one. So in R, we kind of get, this is in Python, what you see here on the right, but you know, it's both notebooks are done in RStudio. This is what is the results. And similarly, we get similar, relatively good results approximation with R. The images are choppy because they're like 200 pixels. You know, in order to have the computations quick enough, I use relatively small images. So basically, this is it. So everything I mentioned here was I just demonstrated, and this is the short introduction of the talk. So I'm going to do quite a lot of hand waving here in details, but not much. You know, I think the biggest secret or the biggest guest or whatever. Actually, the biggest secret is still coming up. The biggest secret is coming up next then. All right, so why I'm doing this in first place? In general, I'm very interested in comparing methods, but to some extent, the approach I have shown you is pretty much because of me starting to use R and attending RStudio's conferences. The first conference was here in Orlando, where I live in Florida. And so I started using, I was using monads before that, but I started using monads or pipeline symbols after that quite a lot. The other is that because of my exposure to R, I became very interested in implementing similar objects. Like now you can have matrices or data frames or whatever with named rows and columns. So after I implemented those objects in Python and Mathematica, and quite a lot of the monadic things I've been doing, I've been utilized for latent semantic analysis. I've been using this kind of object, which comes from the R and S language culture. So here, I don't think I'll have much time to discuss this additional topics, but I would like to mention you can find all these links in this GitHub repository. I made a special GitHub repository for this presentation, and there are quite a lot of references and some other elements you can find, and the notebooks themselves, of course. All right, so I'm going to go through more details here. First, I would like to mention something about the random mandalas. There's like let me give you. So I initially implemented the random mandalas in Mathematica. So this is what you see here, Mathematica. We'll be decomposing this kind of mandalas, not these kind of mandalas. The other is that I need to invert those mandalas. I need to make them white on black, black meaning no pixels, 0 pixels. So there's some inversion you are going to be seeing in the notebooks being done. I'm a big proponent of informed hate, and very often people dislike Python or dislike Mathematica or dislike R, or tell me why I'm not using Python, why I'm not using R, why I'm using R, or why I'm not using Mathematica, and so forth. I'm very interested and eager, anxious, willing to compare this kind of system. So back to informed hate or whatever. So here I implemented more or less the same functionality in Python. This is what you see here. And so if any of you is enthusiastic about Python, you can look at this package here. It has some of it corresponds more or less fully to my Mathematica implementation. All right, so after we have created the mandala collection, so I'm going to move here. So I want to do this, as I was mentioning, and sorry, I'm moving probably between screens too much. I want to share the same data across all three systems, right? Mathematica, Python, and R. So I could have created the data, say in Mathematica, and exported them in some data package or something like that, or exported them in some repository. Well, it's more elegant to actually have a package which generates the mandalas. We just use the same random seed on all three systems. And what is nice is that both R or RStudio, and Wolfram Research, they have made very nice interplay between the, say, R and Python and Mathematica and Python. So we're going to leverage this. And so here you can see in one detail here, which I would like to mention. I actually like RStudio for several reasons, but when I do stuff in Python, I do package development in PyCharm, but I do data science research in RStudio. If I make presentations, I do use Mathematica for presentations. I try to avoid Jupyter as much as possible. So here, back to this, what is happening here. These are Python cells, right? If you don't believe me, I can show you the actual IDE. This is the RStudio IDE. You can see I have started my Python cells and so forth, right? So I'm executing Python. At some point, the mandalas which are generated in Python, I'm going to move them into R. This happens with this pi $. This is the magic part here, which comes from using the package reticulate. All right, so we got the mandalas. I'm just verifying that I get the same mandala. Since I said it's going to be a comparison, let's do the parallel walkthrough with Python here. And I think I zoomed my so yeah, I have created my mandalas and I'm processing them now. So here we can see what we have the same. Well, actually, I didn't plot the sample here for whatever reasons, but we do have the same dimensions. We do have 512 mandalas, and and I have flattened them into. I have made these inversions here, and as I mentioned earlier, I have converted them into white on black instead of being black and white. One interesting point here is what I need to use this transparency argument. Otherwise, this conversion is not going to be that good, and it's going to make the computations more difficult. Next, we are making the related semantic analysis objects. So you can see here, this is the monadic pipeline in R, right? Like what I was saying, but I saw being demonstrated in the studio conference in Orlando. In Python, this more or less looks kind of the same, but instead of monadic pipeline, we have this dot point. Then we applied. I have created my pipeline here. Sorry, I jumped ahead. Created my related semantic analysis objects. How well do you see this? And now I'm doing the singular value decomposition. I didn't have time to put in the non-negative matrix factorization here in this notebook. But of course, I have done it also in Python. I'm going to expand more on that. These algorithms were they're kind of the same, but also fairly different. And I'm going to use this opportunity here to demonstrate that. If I figure out where is my Mathematica notebook for doing this. And so just a moment. So somewhere here. Imagine I have this set of points, right? So I need 3 coordinates to describe them. But obviously, if I rotate my coordinate system in a certain way, maybe I just need two coordinates to describe it. More or less, this is what singular value decomposition is doing. We're finding a new coordinate system in which this original data set needs less dimensions to be represented. That's why it's called dimension reduction. Independent component analysis is very similar. I have not implemented it in Python, but it is implemented in Mathematica. And this is the non-negative matrix factorization. It also produces a basis for describing the points, which is a smaller basis, but the points, what you see here, they're positive. The vectors, the tips of these arrows, they're positive in the positive quadrant or octant in this 3-dimensional space. This is very important if we try to interpret data, especially say coming from interpret topics and dimension reduction, especially if it comes from dealing with natural text. So we can see how is this going to work in with Mandalas. So the singular value decomposition, it's kind of just by the name, singular value decomposition. If you're familiar, you find the top, you find the singular values, they're kind of calculated in descending order. So what I was mentioning in my 3-minute quick review, we have this average mandala. Some people can tell me, look, why you're calculating the average mandala? Obviously, this is a clear outlier. Why not just subtract this average mandala to begin with from the data set, and then everything would have started from probably somewhere here. For bureaucratic reasons and computer science reasons, I think it's better to do it this way. Also, I have experimented with this type of approximation. It's not particularly better, not with the contemporary computers and computational sources. So this is the deconstruction I'm talking about, I want to talk about. We have the average mandala, and this mandala, as you can see, there with increasingly more detail. So basically, I'm claiming that I can represent any mandala I haven't seen as this one, the average one, plus some weighted addition of all this here. And you can see they become increasingly more detailed, right? So this is one of the ideas. Alternatively, and this is the non-negative matrix factorization, how about finding all of the independent ingredients in these mandalas? Like this is this kind of rotational symmetry you can see. And I'm claiming something else here. I'm saying, if you give me a mandala I haven't seen, I can combine these elements in one way or the other, probably with some weighted sum, and then construct the mandala. So it's actually quite different. It's a different type of approximation. Okay, so let's actually see the approximation itself. Yeah, I'm generating some mandala here. If I go back to my Python, yeah, you can see in Python we got the same basis, right? Which is in R, which is encouraging, right? And then here I'm generating a new mandala, right? And same in Python with the same random seed, right? Same Python command for generating mandalas. And unfortunately, how come? Oh, okay, yeah. So here, this is how it looks after the processing. The processing of the test mandala is the same we did for the training set. And then I actually try to decompose it according to the singular value decomposition basis, right? So I'm going to use opportunistically here the basis from Python, right? So basically I'm saying here, look, this mandala I haven't seen before. I need to use this weight for the average one. I need to use this corresponding weights for the mandalas, for the correction mandalas here. And then if I put them on top of each other, I'm going to get something which resembles the original mandala. And this seems to be the case. I mean, you can see it's kind of fuzzy, it's not necessarily great, but it actually has quite a lot of the elements in this mandala we haven't seen. All right, so how this is going to work with non-negative matrix factorization? Well, more or less absolutely the same thing. But this, the basis here, it's different. And because it's non-negative, well, although I have negative weights, we can deal with this in some way or the other, but this is coming from this algebraic method, which I'm going to, if we have time, I'm going to discuss a little. So anyway, we get the same approximation more or less, right? I mean, we can approximate it with non-negative matrix factorization. All right. So so let me to kind of return to this diagram. Yeah, we went through all of this except we didn't show independent component analysis and we didn't show Mathematica. I'm going to show you the Mathematica notebooks, right? So yeah, you can see this is my Mathematica notebook. This is the Python code notebook. Pretty much everything is the same, or not. I simply forgot to calculate. To run the calculations in Mathematica, which I'm going to very quickly try to convince you that I have Mathematica implementations. Let's go in this repository. I have this notebooks Wolfram language, and I'm going to click on this one, which is with the methods in Mathematica. And here we see more or less the same basis, the same things, same results being produced. And yeah, you can see here the independent component analysis produce something interesting, right? It's kind of in between. It's kind of in between the non-negative matrix factorization and singular value decomposition. There's an average one, but you can see there's not this kind of decreasing detail. Yeah, then again, you know, I use the same random seed to generate unseen mandala in Mathematica and then approximate it and approximate it and approximate it. All right, so more or less this is it. I did want to mention a couple of other things related to this. One is that if we do, just a moment, yeah. Imagine I apply this to the famous MNIST dataset. This is the handwritten digits dataset, right? So, I mean, I applied it only to the fives here, or I applied it to all digits, right? But you can see you have the same thing, right? We have the average 5, and these are corrections on this average 5. This is what this basis with singular value decomposition is. Alternatively, if I use non-negative matrix factorization, I can claim that these are different ways people kind of write 5s. I mean, I can see it in this way. Or some archetypical people, you know, writing archetypical handwritten 5s. This is what is happening. Now, what I'm doing, I'm applying these two procedures for each of the digits I have. And then this approximations I was showing, the residual, the difference between these two images. I can use this residual to do classification. The smaller the residual, the more likely the handwritten digit belongs to the digit in question. And so you can see this is the confusion matrix with this classifier based on this type of decomposition. You can see that say 8 has been confused a lot with 2 and 3, which makes sense, and 5, because 2 is a subset of 8 and 3 is a subset of 8, and same with 5. All right, so I would move to further topics here. I'm not sure. Rachel, how are we with time? I can finish it here.
We're good, but just while you're showing that, I think someone had a question too on how you actually created this table of contents here.
This thing, this is a MindNote application. I have not been updating it for a while. This is from, say, almost 8 years ago. There is a new version which I don't like, and I'm trying to actively figure out what else I should be using. But yeah, I mean, this is using this mind maps, especially if I have multiple projects comparing different languages. This is one way to do it.
Cool, thank you. We're good on time too.
Okay, so then the next, the biggest secret, right? The biggest secret needs to be reloaded. Just a moment. So, all right. So this here, what you see is a shiny app, right? So what is? Let me explain a little bit. So I'm using. I have an account on. Let me see. I have an account on Shiny Apps, right? IO. This is a service provided by our studio. I'm also renting a server at DigitalOcean. If you haven't heard DigitalOcean, yeah, you can, like, I rent it for $20 a month or something like that. So I have my own server on DigitalOcean. On this DigitalOcean server, I'm running the Wolfram engine. I'm running some other, some other software with a language called Raku. And whatever this service is, I have connected it to this Shiny app on my account in Shiny IO. And why this? So you can see if I press this submit button, right? This generated code for data wrangling. If you know data wrangling, if you know tidyverse, this is what is happening. So here I'm going to do latent semantic analysis, and I'm going to copy and paste this latent semantic analysis here, pressing the submit button, and you can see this is in R. This is the R code which I use for the latent semantic analysis. What I was showing earlier here, right? These pipelines you see here, right? Like this creation pipelines, where basically this is what is being produced. Now, if I want, I can also do this in Python. This is the object orientation perspective, right? Or in Mathematica, right? So Mathematica, yeah, this needs to, probably it's going to make more sense if I copy and paste it here, right? So this is my monadic pipeline symbol is something else here. All right, so ideally, this is the other reason I'm showing this. When I make this kind of comparisons, this is the alternative way of showing the comparisons is, but we have a common workflow, and this common workflow has been utilized across all of these programming languages. What is the common workflow? I actually forgot to bring up that particular diagram, but I'm going to find it here, right? So I'm going to open this image in a new tab. So this is another way to see what we did. We started not with text data, we started with image data, but we process this image data, we put it in some multidimensional vector space, linear vector space representation. Then I did the latent semantic, I didn't actually do latent semantic indexing functions, but I just went through with the topic extractions, given some parameters like non-negative matrix factorization, etc. With the extracted topics, we displayed them, displayed some interpretation of them, and then we did something else, right? Okay, so now I'm done.
Thank you so much, Anton. I was just scrolling through to see if there were any questions that I had missed earlier, and just jumping over to Slido too.
Okay. While we're waiting for Rachel to find questions, I'm going to generate some mandalas in Mathematica, in case, if I do something like, there's a single mandala mode and a multi-mandala mode, right? So if I put something like, say, like this, if I put multiple radiuses, then the multi-mandala mode is going to kick in, and I can say something like color function and say, what is a good color function? Say bright bands. Okay, maybe this was not a good dark bands then. Okay. Anyway, now in Python, pretty much works the same way, right? So here I have some random seed, but let me change this, and every time. So I'm using my color mapping here. It's somewhat different. I personally really don't like this library matplotlib, but well, I have to live with it, I guess. The difference is obvious, probably, especially with this zoomed part. I mean, I need to procure images from Python into Mathematica, and this is what you see here, very native graphics. So it's a different. That's why they're kind of prettier and more saturated, I guess, and so forth, right? One of the things I would like to mention is that the deconstruction of the mandalas is that it's a little bit, it's kind of hinting how the mandalas were created, right? So if I go, no, not the, we can discuss this, but I don't think it's that interesting. So there's when I generate the mandalas, there are two approaches, right? One is to start with, to make the a segment and then do rotational symmetry. This is how I was showing. Now, the other approach of generation is to make this radial elements. So the mandalas I have generated here, which I was showing, they're created with this radial symmetry part. Maybe it's not that obvious here, but what is interesting is that when I apply the non-negative matrix factorization, the basis goes to the other approach, the alternative approach of having layers of concentric mandalas. Let me see, do I, these are with the rotational symmetry. These are the ones made with concentric layers. All right.
Anton, one question I had is, I know a lot of us are probably from teams where we are using a bunch of different tools, or at least definitely are in Python. But I was just curious how you work together with other people across the team. And I know you mentioned you used Reticulate before, use Python and R together, but
very good question. First of all, why I'm using R and not Mathematica? I mean, it's not clear, probably. I didn't introduce myself that much, but I work for Wolfram Research. I'm a power user of Mathematica. Maybe I'm a power user of R, I don't know. But I know I have used Mathematica for nearly 30 years. Now, probably for 10 years, but I and Mathematica are very similar when it comes to as programming paradigms. And so, especially compared to languages like Python. The reason I'm not using Mathematica is that with Mathematica, sometimes it's very hard to walk the last mile. I really like this shiny apps perspective, I mean, if I just want to have some computational interface to some web service, which is what is happening here with this URLs and whatnot, right? I'm just constructing some URL and I'm calling the web service. Well, this is unbeatable. It's really hard to beat. But then again, like when I actually want something very interesting to be happening, mathematically complex or something to figure out, I still go to this Wolfram engine. So what I'm saying here, well, I make interfaces like this. So I apply or utilize a variety of technologies and then basically, try to solve the problem which we have in our teams. And if they like the solution, right, I might want to go in one direction or the other, accentuating some of the whatever technology is most convenient. I'm sorry, this was probably a lot of blah blah, but yeah, basically this is it.
No, that's helpful. Right tool for the job. I see Libby has her hand raised too. If you want to jump in.
Yeah, Anton, I was curious, you said that you used the residual, like subtracting from the average in order to classify, so you could actually have a confusion matrix for this. I was wondering how you decided on a cutoff for that residual, on what constitutes a hit or what constitutes a miss.
Great question. The thing is that you don't need to decide on the cutoff. I mean, if you want to do, this is like, let me, handwritten. I have several of the, handwritten, just handwritten. Okay, so there is like this one, and there's this one, right? So this is more or less what I was showing earlier. Okay, so this one here, this is a very old post, which my training set was just this, right? And my testing set was this, like thicker and thinner digits. So basically what is happening is we make these images, two-dimensional images. We make them one-dimensional vectors. You can see, I just say by columns, I have, unfolded this. So I make these vectors here, right? Now, okay, let's open this image here. So when I do the residuals, you can see I'm just letting them compete, right? So I have given this digit to all these 10 classifiers, right? Or 10 singular value decomposition approximators. And whoever produces the smallest residual wins. And so similarly, you can see, for example, like this 7 is very non-typical given my small set. 9 was the winner, right? It wasn't recognized as 7. And you can see, like say 5, often enough, this particular case can be confused with 3, but it can be also confused with 8 and so forth, right? So basically this is it. This here with 8, it was classified as 8, but you can see 2 was a close contender and so forth. So if I want, I might decide for each of these particular digits to find a cutoff criteria given what are my testing sets, but I haven't done that. I'm just doing this on the get. To some extent, that's why I'm using this approach. I don't need to train it that much, and I'm already getting somewhat good results, right? Whatever confusion matrices I was showing here. If I want to be a little bit more precise about this, it's like I can. So this is an old post which compares the singular value decomposition of principal component analysis, non-negative matrix factorization, and independent component analysis, again over Mandalas. And here I'm actually applying different kinds of noise on, say, 2 types of digits. It's like 7 and 6, right? And then I try to see how these classifiers, based on the different topic decomposition, right? How successful my classifier is. And if I can show you this here, I'm using a machine learning algorithm to figure out which of this denoising, because when you do dimension reduction, it's some sort of denoising procedure, right? So basically, I'm trying to figure out which of this is going to be more relevant. This is probably here. I might try to be finding what is the number of topics, what is the how many steps, and etc. Right? But for this classifier with the handwritten digits, I didn't need to do that. Hopefully it makes sense.
That was super helpful. Yeah, no, that makes total sense. Having them all run through each digit and then just taking whatever had the lowest residual and using that as your category.
Right.
That's fantastic. Thank you so much, Anton.
Yeah.
Thank you so much, Anton. I know we're a little bit over on time, but just want to double check that there weren't any questions I missed, or if anyone wants to raise their hand and jump in too. Anton, would you be able to share these slides with us as well?
All of this is already in GitHub.
Okay.
So if you go to this GitHub repository, which is, I already posted the link in the chat.
Perfect.
Yeah, you'll find the notebooks. You'll find this HTML notebooks I was just showing, and then you'll find the Mathematica notebooks. Actually, I need to update the Python one, but basically everything else is already there.
Okay, awesome. Thank you for sharing those. And I'll just put the Meetup link in the chat right now. Yep. So the slides Anton mentioned will be there in the discussion, and I'll put the Libby's there and then the recording too.
Right. Yeah. So all this what I was showing here. Yeah, it's in there's a main directory, right, for the presentation, and there's a concrete one in right, the R project.
Yep.
Then
perfect.
Other stuff. Mm-hmm. All right.
Awesome. Well, thank you so much, Anton, for the presentation, and thank you, Libby.
Thanks for inviting me. Yes.
Thanks, Rachel. Thanks everybody who came.
Yeah.